Hey, geometry students. In this lesson, we are going to be learning about parallelograms. And actually, this is the second lesson of the year where we're going to be learning about parallelograms. You may remember, probably not, but you might remember way back in lesson 34, we learned about the properties of parallelograms. In this lesson, we're going to be learning about identifying parallelograms, determining, proving that a quadrilateral is a parallelogram. Now, here's an interesting thing. In this lesson, we don't have theorems. We just have statements of properties and identification. Okay. So just take a look at one of these. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. In other words, if I can show that both pairs of opposite sides, in this case, MP is congruent to NQ, MN is congruent to PQ, I can state by the properties of parallelograms that I have a parallelogram. Here's another property that can be used to identify. If both pairs of opposite angles are congruent, it's a parallelogram. Okay. Hey, let's just pause for a second. Do you remember that all rectangles are actually parallelograms and all squares are actually rectangles? So both rectangles and squares fit the definition of a parallelogram. Opposite sides, pairs of opposite sides are congruent. You can kind of picture that for a rectangle and a square. In a square, it even has the extra benefit of all of the sides being congruent. And then the opposite pairs of angles are congruent, except in a rectangle and square, they're all the same. All of the angles are the same. They're 90 degrees, but you could still say that opposite pairs of opposite angles are still congruent. So just wanted to remind you that both rectangles and squares will also fit these identifying properties. And then lastly, this is probably the most difficult one to visualize. If one pair of opposite sides of a quadrilateral is congruent and parallel, then you have a parallelogram. So you don't even need to prove something about both pairs of opposite sides. If you know that one pair of opposite sides is parallel and congruent, what that does is it forces the other pair of sides to be parallel and congruent, which also makes it a parallelogram. Hey, before we begin, one other thing I didn't put on here that I maybe should have is the definition of a parallelogram. What is a parallelogram? A parallelogram is a quadrilateral that has two pairs of opposite parallel sides. Okay, so the opposite sides in a parallelogram, both pairs of opposite sides are parallel to each other. Now, back in lesson 34, we learned these properties of parallelograms. We learned that opposite angles are congruent, consecutive angles are supplementary, opposite sides are congruent, and the diagonals bisect each other. Notice I put two of those in blue. That's because two of these, you'll notice, are repeats of our identifying properties. We can use those two to say if they're true of a figure of a quadrilateral, that quadrilateral has to be a parallelogram. The other two are just properties that parallelograms have. So if we can prove that something is a parallelogram, then we can state these two that are in black here about that figure because it's a parallelogram. But those ones don't prove that it's a parallelogram. Okay, you're going to like this because this simplifies proofs immensely. Um, Normally, what we would have to do with a proof of the parallelogram is like break it, draw the diagonals, and break it apart to triangles, and then prove that the triangles are congruent, and then use CPCTC to show that different parts of the parallelogram are actually congruent to each other, or different parts of the diagonals. It was just a lot of work. You could do things that way. You can still do things that way, and it works, but it's a lot more ink that you have to put down for the proof. We're going to keep things simple here. I'm going to show you how you can use these properties and proofs to immensely simplify your proofs with parallelograms. All right, so we're going to start off with letter A. In quadrilateral ABCD, AD, segment AD is congruent to segment BC. And I'm just going to note that the way this is written, AD and BC are opposite sides. AB is congruent to DC. AB and DC have to be opposite sides. I need to prove that the diagonals bisect each other. Well, watch how easy this actually is. Okay, so this is letter A. And we're going to do step one. Now, normally for step one, I'm going to skip a step here just to keep things a little simpler for our video. Normally in step one, you would have to start by stating your givens. So I would say it was number one, given AD is congruent to BC, AB is congruent to DC, and then also AB and DC are opposite pairs of sides of a quadrilateral. Those would be my given statements. Okay, that's what's given in the problem. Now, I'm not going to write those out here because we're just going to keep things simple and quick here. So once I'm given that, the next thing that I need to do is make a statement that this is a parallelogram. Notice it doesn't say anywhere here that this is a parallelogram. But I know that opposite sides are congruent. So I could state that ABCD is a parallelogram by the properties of parallelograms. And I'm going to say in parentheses, opposite sides congruent. Okay, just to note which property I'm using. And you're going to like this. So the last step in my proof is that the diagonals of ABCD bisect each other. Now that I've proven that it's a parallelogram, I can just state any of the other properties of parallelograms are true. And what is one of our other properties of parallelograms? Or from lesson 34, we learned that the diagonals of parallelograms bisect each other. So I'm just going to say that it bisect each other by the properties of parallelograms. And that's it. I'm done with my proof for letter A. On to letter B. Not all of these are quite this easy, but man, that was easy. All right, letter B. In quadrilateral EFGH, angle E is congruent to angle G, and angle F is congruent to angle H. Prove that the opposite sides are congruent. Okay, so again, I would state my givens first. I have quadrilateral, so given quadrilateral EFGH, the opposite angles are congruent. Angle E is congruent to angle G. Angle F is congruent to angle H. So I would state that EFGH is a parallelogram by the properties of parallelograms. And in this case, I'm going to parentheses opposite angles congruent. And then I can just state, now that I've proven it's a parallelogram, I can state any of the other properties of parallelograms. In this case, I'm going to state that the opposite sides are congruent. So I'm going to just opposite sides are congruent. I could be more specific and say EH is congruent to FG, EF is congruent to GH if I wanted to. I'm just going to state opposite sides are congruent by the properties of parallelograms. Easy, right? Well, not all of them are quite that easy. Let's take a look at letter C. In letter C, we have quadrilateral WXYZ, and we have two triangles. We draw one of the diagonals here, and we split it into two triangles, and it's given. Okay, so I would again state given triangle WXY is congruent to triangle YZW. I need to prove that this is a parallelogram by showing that WX is parallel to ZY and WX is congruent to ZY. Okay, so one of the things that I would do to prove that these are congruent, I'm going to use CPCTC here a couple of times. So first of all, I'm going to state that angle ZYW is congruent to angle XWY. How can I say that? Well, if they are truly similar, they're congruent triangles, right? So this is by CPCTC. Those are corresponding parts. This angle Y here and this angle W are corresponding parts of congruent triangles. So they have to be congruent to each other. But wait a second. If I've proven that, oh, and that should be number one here. Okay. And then number two, is going to be that WX and ZY are parallel. And the theorem that I'm going to use there is the converse of a theorem that we've used a long time ago with transversals. So let's see, those, what kind of angles would those be? Those are alternate interior angles. So this is going to be proving that they're parallel by the converse of the alternate interior angles theorem, which states if two lines are cut by a transversal and the alternate interior angles are congruent, then the lines are parallel. So that's, I'm just going to state that that's theorem 12.1 because I just looked that up. But that's the converse of the alternate interior angles theorem because I proved that the alternate interior angles are congruent. Okay, so the next, now I've proved the lines are parallel. The other thing I need to prove is that WX is congruent to ZY. That's really easy. I could state that WX, segment WX, I should just be clear about that. Segment WX and ZY are congruent by CPCTC because they're corresponding parts of congruent triangles. They're both the bottom leg of this triangle, or I guess the top leg of this triangle, but they're the corresponding parts of a congruent triangle, and therefore they're congruent. So now, number 4, I could say that WXYZ is a parallelogram by the properties of parallelograms. I'm just going to say parallel, congruent, opposite sides. All right, so we use the third property here to prove that this is a parallelogram.